Let's look at how to solve homogeneous linear equations with constant coefficients. So we know that this is the general form of a linear ODE. But in this case, the linear ODE has constant coefficients. That means an is just a constant, an minus 1 is also a constant all the way to a0. And it's homogeneous because our normal g of x is now 0 right here. All right, let's start with the first order. So a first order constant coefficient homogeneous equation would look like this. Say a1 y prime plus a0 y, right, is equal to 0. We've solved this before. This is first order equation. We know how to solve it. It's linear. It's at the same time, it's also separable. So maybe we should just solve it as a separable linear equation. So there are several methods. So the first method is let's say method 1. Call it method 1. And if let's separate variables. All right, treat it as a separable equation. So if you write it as a dy dx, a1 dy dx plus a0y equal to 0. This will lead us to having, let's see, we have dy, so a1 dy dx is equal to negative a0y. So this is an error. So we end up with dy over y is equal to negative a0 over a1 y. So this is separable, and we can write it as, we can take the integral of both sides, 1 over y dy is equal to negative a0 over a1 y. Let's take the integral, not y. No, there is no y. Dx, that's what I wanted over here. Sorry, this is dx. All right, and this is now integral dx. Okay, so this will end up with, let's say, this is natural log of y is equal to minus a0 over a1 x, right? And this tells us that y is equal to e, or maybe plus some constant. Let's say plus some constant c. So this is going to be e to the, this is going to be e to the c times e to the negative a over 0, a over 1 x. Or we can just write it as, instead of writing this as e to the c, we can write it as c. Let's just change this to be c. All right, so this is how we know how to solve it, by separation of variable. And we can also do it as a linear equation. How about, I'm going to introduce a new method here, call it method 2. So method 2, we're going to go by observation. I don't have a name for it, so I'm going to call it the name observation. So what are we observing? We observe that if we rewrite the equation as a1y or a prime y, right, So this is supposed to be a1, sorry. a1 prime plus a0 y equals 0. We can rewrite it as y prime is equal to negative a0 over a1y. Okay, so if we observe, we see that there is only one function that has this property. There's a function that has the property of when you take its derivative, you get that same function times a constant. So for instance, if you see e to the power of, let's say, 2x, if you take its derivative, you get 2 e to the power of 2x. If you now have 2e to the power of 2x, if you take its derivative, you get 4e to the power of 2x, and so forth. So you always have this e to the 2x in any derivative you take. Take the derivative of this, you get e to the power of 2e to the power of 2x. Take the derivative of 2e to the power of 2x, you get 4e to the power of 2x. So we have that the derivative of e to the kx, or e to the something x, is a constant times e to the something x. So we're going to make a guess. Our guess is that our y has the form of e to the rx. All right? So guess. Y has the form of e to the rx. So if y is e to the rx, then we have that y prime, so y prime is equal to r e to the rx. Okay? Now, if y prime is r e to the rx, our equation, I'm going to call this equation star 1. Our equation star 1 becomes, we plug y prime and y into the equation, we get r e to the rx, a1 r e to the rs, plus a0 e to the rx, and this is equal to 0. If we factor out e to the rx, we end up with a1 r plus a0 equal to 0. This is never equal to 0. E to the rx is never equal to 0. So that means that this has to be equal to 0. This must be equal to 0 because the product of this quantity and e to the rx is equal to 0, and we know that e to the rx is never equal to 0. So this quantity has to be equal to 0. And if it's equal to 0, it tells us that r is equal to a0 over a1. Okay? So, or negative a0 over a1. So what do we have? We said that y has the form e to the rx, and then we now found out that rx is negative a0 over a1. Therefore, our general solution is y is equal to c1 e to the negative a0 over a1. Right? Just like we got there. Okay? So, let's review what we did. We guessed that the equation has the form e to the rx. The solution has the form e to the rx, right? And we ended up with the general solution c1 e to negative a0 over a1 x, actually. X. Did we have x there? Yeah, we have x. Yeah, so our r is a0, a negative a0 over a1. Okay, so that's first order, and this, we don't actually need this method too, because we can solve it as a linear equation, we can solve it as a separable equation. So, but we are doing this because we want to motivate ourselves to solve second order equations. We want a second order homogeneous equation with constant coefficients. So let's call it a y double prime, maybe a2 y double prime. Let's just call it a. Instead of a1, let's use b y prime plus c y equal to 0. Okay? And here a, b, and c are all constants. Again, let's assume that our solution has the form, that y has the form e to the rx. And why are we doing it? Because we're motivated by what we found out here. So if we do that, then y prime is r e to the rx, y double prime is equal to r squared e to the rx, right? So plug this back into, I'm going to call this asterisk 2. So asterisk 2 becomes a r squared e to the rx plus b r e to the rx plus c e to the rx is equal to 0. Now, you can factor out e to the rx. Then we'll be left with a r squared plus b r plus c is equal to 0. So if we know that this e to the rx is never equal to 0, so if we can solve this for r, once we get our r, we plug it in here, and then we have our solution. If we solve r and r is equal to 2, then our solution is y is equal to maybe a constant times e to the 2x. Okay? All right. And why am I putting a constant there? Because if e to the rx is a solution, then any constant times e to the rx is also a solution. And we know that from the theories we studied before, maybe in class, we know that if f1 is a solution, then c times f1 is also a solution. If f1 and f2 are solutions, then c1 times f1 plus c2 times f2 are also solutions. All right, so this, we call this the characteristic equation. Characteristic equation is also called the auxiliary equation. All right, so now let's go ahead and see what could happen if we solve this equation now. If we solve I don't want this. If we solve ar squared plus br plus c, solve the auxiliary equation equal to 0, we could end up with we're going to end up with two solutions. This is a quadratic equation. We can end up with r is equal to r1 or r is equal to r2. Okay? Whenever you solve a quadratic equation, you get two solutions, r1, two roots, it could be r1 and r2. All right, so let's look at different cases. Let's look at case 1. The case 1 where r1 is not equal to R2, and both of them are real numbers. Okay? In that case, our solution, the general solution, will be y. We know that the general solution is y is equal to e to the r1 x. But since r is r1 or r2, so it's going to also be plus e to the r2x. And then we put constants c1 and c2 because of our theory. We know that the linear combination of any two solutions is also a solution. All right, so that's the second case. And why are we doing this? Because these two functions, e to the rx and e to the r2x, form form a fundamental set of solutions, and they are both linearly independent. Assuming r1 is 1 and r2 is negative 1, e to the x and e to the negative x are linearly independent. Okay, so this general solution makes sense based on the theory we learned so far. Let's look at case 2, a second case, where r1 is equal to r2. And let's just call it r since they are both equal. And it's a real number. It's not complex. And I'm going to write a general solution here. The general solution is going to be c1 e to the rx. You could call it e to the r1x. All right, you could say c1 e to the r1x plus c2 e to the r2x. But since r1 and r2 are the same thing, this just becomes c1 plus c2 e to the rx, right? We don't want this because this is just one solution. We want two different solutions that are linearly independent, right? And then the general solution will become a linear combination of these two solutions that form a fundamental set, right? So let's go ahead and try to change things up a little bit. So I'm going to do this. I won't explain a whole lot, but the solution x e to the rx, since r1 is r, let's just call this r, e to the rx, right? So if it's the same thing, if r1 and r2 are the same thing, you have the first solution is e to the rx, the second solution is x e to the rx, and then the general solution is going to be a linear combination of both of them. This may not make sense to you, but I'm going to explain in another video why this makes sense. Okay? So let's go ahead and look at case 2 or case 3. Let's say R1 is equal to alpha plus I beta. So R1 is a complex number and R2 is its conjugate, alpha minus I beta. Okay? In this case, the general solution is y is equal to e to the alpha x times c1 cosine beta x plus c2 sine beta x. All right, you probably have a whole lot of questions now, but I will explain this in another video. So the first one is pretty clear. Case 1 is pretty clear. Case 2 The first part of it is clear. The second part is not that clear. Case 3, it almost looks like everything is not clear. But trust me, this is the right solution. And I'm going to discuss it in another video. But something that I want to point out is that in each case, the two solutions that has a linear combination that gives us the general solution. In other words, for instance, in the first case, e to the r1x and e to the r2x are both linearly independent. So what am I saying? We know about the Wronskian. So it turns out it's always going to turn out that the Wronskian of e to the rx, e to the r1x, and e to the r2x is never going to be equal to 0. In this case, the Wronskian of e to the rx and x e to the rx is never going to be equal to 0, showing that they are linearly independent. And you can always show that the Wronskian of cosine beta x and actually, let's do it this way, of e to the alpha x cosine beta x and e to the alpha x sine beta x is never going to be equal to 0, showing linear independence. Okay, so let's remember these solutions, that this implies that, and that this implies this, right? And this implies that. Let's go ahead and do some examples. All right. Example 1. Let's solve 2y double prime minus 5y prime minus 3y is equal to 0. Okay, now let's look at this. When we have ay double prime plus by prime plus cy equals 0, our characteristic equation is ar squared plus br plus c. So now that we have 5y double prime minus 5y minus 3y minus 5y prime minus 3y, our characteristic equation is going to be 2r squared minus 5r minus 3 is equal to 0. We're going to solve that quadratic equation. I'll teach you how I solve my quadratic equation. It's pretty slow and a little crude, but it's very a little, I want to say primitive in the math sense, that it takes its time and it's very fundamental. So I start by saying 2 times negative 3. 2 here times negative 3 will give you negative 6. I want to find two numbers that when I multiply them together, I get negative 6. But when I add them together, I get negative 5. Right? What numbers are those? What numbers are those? So, I'm thinking 6 and negative 1. No, actually negative 6, positive 1. When I add them, I get negative 5. When I multiply, I get negative 6. And then we come here, we rewrite this as 2r squared minus 6r plus 1r. So I replace minus 5r with the two numbers, negative 6. Replace negative 5 with the two numbers, negative 6 and positive 1, and I'm left with 3 equal to 0. Go ahead, factor out the 2r from this part. Factor out the 2r, you're left with r minus 3. And then from here, you factor out a 1 because you want to get r minus 3 also there. Now you have two terms. The first term and the second term, and each of the terms, r minus 3 is common. And they have 2r plus 1 is common. So this is pretty slow, but I'm sure by now some of you already just looked at it and we're just able to factor it without thinking. So this shows us that r is equal to 3 or r is equal to -1/2. Okay, so we have r is equal to 3 and r equals to -1/2. And remember, when we find our r, the two r's here are both reals and they're not equal. So this is our general solution. So our general solution becomes y of x is equal to c1 e to the 3x plus c2 e to the -1/2 x. All right, that's our solution. Okay, so let's try another one. Let's try y double prime minus 10y prime plus 25y is equal to 0. All right. So how do we go ahead doing this? We want our characteristic equation is going to be r squared minus 10r plus 25. So this is r squared and this is equal to 0. R squared minus 5r plus 25. I'm doing my factoring. There's probably other ways of factoring it. R minus 5. So we can almost see that we get 5 twice. So this tells us that r is equal to positive 5 twice, right? So this means that our general solution is y of x is c1 e to the rx, e to the 5x, okay, plus c2 x e to the 5x. Okay, so I want to give you some to do. We're going to end there. I'll list a few that you can do. Number 3. Let's try this. Number 3. How about y double prime plus 4y prime minus 7y equals 0? And then let's see, how about the IVP, initial value problem? Y double prime minus y prime plus 1 over 4y is equal to 0. Y of 0 is 2 and y prime of 0 is 1/3. Okay, then I'm going to give you third order y triple prime. I want you to just use the same method and see if you get something and if your answer is correct. And number 6, I think that's it. Just 3 of them. I'll see you in class, or I'll see you in the next video.